Okay, so when I get the products for these reactions, the first one is a 2-carbon alcohol reacting with a 1-carbon carboxylic acid, and a 2-carbon alcohol is known as ethanol. A 1-carbon carboxylic acid is known as methanoic acid or formic acid. So just drawing the carboxylic acid first. If you react an alcohol with carboxylic acid, you'll get an ester, and this is going to require the use of an acid catalyst, using a strong acid like hydrobromic acid or hydrochloric acid or sulfuric acid. And the oxygen of the ketone is going to deprotonate the acid. And this occurs because it's able to undergo resonance, meaning that the conjugate base of this is going to be more stable, and it's going to lead to a favorable reaction. If we try to protonate this, or if we try to protonate the oxygen of the alcohol, we wouldn't have resonance, and therefore wouldn't be as stable. So the oxygen of the ketone is going to grab proton, and as a result, it's going to make this carbon more electrophilic. And this needs to occur because the alcohol isn't a good base, so we need to protonate the oxygen first in order to make the carbon even more reactive. Otherwise, this wouldn't react as fast. That bond's going to break. And we'll get the addition of this group. It's in a pair of electrons, so now it's a positive charge. And we still have electrons right there too. And then over here, we're going to get the alkoxide ion. I'm sorry, this should be an alcohol because it grabbed a proton from HBr. And this is an example of a diol. We have 2 alcohols in the same structure. And this is not as stable as a carbon-oxygen double bond. So the oxygen of this alcohol is going to deprotonate ethanol, and as a result, it's going to turn into water, which is a better leaving group because it's a weaker base. The electrons go back there. And once this occurs, once we have the formation of a better leaving group, the oxygen-oxygen double bond is going to reform and expel OH2. This will become water once that grabs that proton. So we have this. This is going to become an ethoxy group. And this using a pair of electrons to reform that bond. As a result, this will break. And this wouldn't form if we didn't have a good leaving group. Like if it was still hydroxide, it wouldn't be able to reform this carbon-oxygen double bond. We have the formation of this ester and also water as a side product. But we still have a hydrogen attached to this oxygen right here, so it's going to have a positive charge. And the last step is for the bromine that was expelled in the first, or those they left in the first step. To just grab that proton from the ketone to regenerate the acid catalyst of HBr. And in this reaction, we need to increase the concentration of the base to favor the formation of the ester. The next one is a 1, 2, 3 carbon alkene with the alkene on carbon 1, and it's reacting with hydrogen gas. So this is propene. And hydrogen gas is an example of a reducing agent. It's capable of reducing ketones and aldehydes, but it's not strong enough to reduce a carboxylic acid or an ester. And it's also done with a metal catalyst like palladium, platinum, or nickel. And it's going to reduce the alkene to an alkane to give us propane. And then for C, it's going to be it's going to be a 4-carbon alkene with the alkene on carbon 1. So it's going to be butene. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, 1 and this is reacting with HBr. And this is an example of electrophilic addition reaction, where this is going to be the lowest acid, the proton donor, and also the electron acceptor. And the alkene is going to be the nucleophile, and this is going to grab proton from HBr. That bond's going to break because it's very polarized. Bromine gets both electrons. And it's going to lead to the formation of the most stable. It's going to put the hydrogen on the less stable carbon so we can get a more stable carbocation intermediate. And this is the one with the most R groups. If we put it on this carbon, we would only have one R group. And an R group is an alkyl side chain that acts to donate electrons to make that positive charge more negative and closer to neutral. So on the first carbon, if we put it here instead, we only have one R group, which is the whole chain to the right, and therefore it's going to be less stable than having two R groups. The next step is for bromine to attack it. And it's going to lead to the product of 2-bromobutane.